Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
All right, let's jump straight into this explainer. For centuries, geometry was entirely defined by strict quantitative measurements, right? We're talking lengths, rigid angles, exact distances. But today, we're unpacking a comprehensive treatise that completely flips the script. We're exploring how mathematics leaped from those rigid angles to the incredibly flexible, yet rule-bound universe of topology. We're looking at a discipline that focuses purely on qualitative properties. Things that stay exactly the same under continuous deformations, like stretching, twisting, or bending, just as long as there's absolutely no tearing or gluing involved. We're going on a highly structured taxonomy tour today, mapping out everything from the foundational history all the way to some mind-bending applications in quantum physics. So we'll start with the foundations of mathematical topology, establish our core structures in invariance, explore the taxonomy and axiomatic formalisms, break down some complex structural theorems and proofs, and then wrap it all up with interdisciplinary applied topology. Section 1, Foundations of Mathematical Topology. Let's really look at the motivation behind this field and see how the focus shifted from quantitative measurement over to qualitative spatial reasoning. If we trace the chronological evolution, you can really see how this discipline builds from early intuitions into rigorous axioms. Back in the 17th century, Leibniz envisioned this theoretical domain he called geometria situs, or the geometry of position. Basically, he proposed an algebra that could analyze positional relationships directly, without having to convert them into numerical coordinates. Then, fast forward to 1736, and Leonhard Euler proves his famous theorem about the 7 bridges of Königsberg. He showed that graph connectivity depends entirely on network topology, completely ignoring edge lengths or geometric angles. By the 19th century, Listing explicitly coined the unified term topology, finally bringing these ideas into a formal mathematical discipline. And then in 1914, Hausdorff established the modern axiomatic foundation using neighborhood systems, which was later refined by Kuratowski. This comparison brilliantly illustrates the core leap of the discipline. We're essentially throwing away the mathematical ruler to understand the fundamental continuity of space itself. On one side, you have metric spaces. These rely entirely on quantitative measurement, strict, real-valued distance functions, where we really care about exact angles and exact lengths. But on the exact opposite side, we have topological spaces. Here, we transition to purely qualitative reasoning. We're focusing on continuous deformations, open sets, and connectedness, entirely without invoking distance. Moving into Section 2, Core Structures and Invariance. Now we really need to build the vocabulary for this new universe so we can understand how structures are preserved under extreme deformation. This is the absolute baseline for modern mathematical analysis. It's what allows us to define closeness without relying on a metric distance. So think of a topological space as a pair. You have X, which is just a set of points, and tau, which is a collection of subsets called open sets. By satisfying just a few simple axioms for the empty set, the whole space, and their unions and intersections, this foundation lets us analyze spaces purely through their relationships rather than their physical measurements. Okay, so the absolutely crucial point here is that if a homeomorphism exists between a coffee mug and a donut, topologically speaking, they are exactly the same object. Formally, a homeomorphism is a bijective continuous function with a continuous inverse. In the category of topological spaces, this is the ultimate equivalence. It means two spaces share identical topological properties, things like dimension, compactness, and connectedness, despite having completely different outward geometric shapes. If you can continuously deform one into the other without tearing, they're topologically identical. Now, manifolds are fascinating because they bridge the gap between our local perception of flat Euclidean geometry and the global, non-Euclidean reality of space. A topological manifold is a space that, locally, looks exactly like standard, flat, n-dimensional Euclidean space. Think about standing outside on the Earth. It looks totally flat locally, but globally, we know it has a highly complex, curved topological structure. By equipping these manifolds with an atlas of overlapping coordinate charts, we can seamlessly apply differential calculus across these complex, non-Euclidean spaces. Up next is Section 3, Taxonomy and Axiomatic Formalisms. Having established the basic language, we can now categorize the exhaustive rulebook that governs these topological structures. Just by defining open sets differently, we can generate all these distinct topological types. They scale from the incredibly coarse, indiscrete topology all the way to the hyperspecific, discrete topology. The trivial, or indiscrete topology, only considers the empty set and the whole space as open, which basically means no 2 points can be separated. On the flip side, the discrete topology considers every single subset to be open. We also have subspace and product topologies for building new spaces, quotient topologies for mapping equivalence relations, and even highly specialized structures like the Zariski topology used in algebraic geometry. It's a massive systematic toolkit, but seeing it laid out helps us realize the sheer flexibility of these rules. Now take a look at how the T0 through T6 separation axioms create a strict hierarchy here. They categorize spaces by their ability to precisely separate points and sets. T0, the homograph axiom, simply asks that at least one point in a pair has an open neighborhood not containing the other. But as we move down the list to T2, the Hausdorff spaces, we demand that distinct points possess completely disjoint open neighborhoods. And this strictness increases all the way down to T6, perfectly normal spaces, where entirely disjoint closed sets can be cleanly separated by continuous functions. Section 4, Structural Theorems and Proofs. Let's see how mathematicians actually wield these axioms to prove undeniable structural laws, distilling two really massive proofs into their core logical steps. Uri-san's lemma is a monumental achievement in point set topology. It guarantees that we can use real-valued functions to separate normal spaces. The theorem formally states that a space is normal, meaning it satisfies that T4 separation axiom we just talked about, if and only if any two disjoint closed subsets can be separated by a continuous real-valued function ranging from 0 to 1. Now, in a metric space, you just use a simple distance function to do this. But in an abstract topological space where distance doesn't exist, proving this requires pure structural logic. Rather than getting totally lost in the equations, just follow this logic. First, we characterize the space via the normality axiom. Next, we inductively construct a nested family of open sets between our two disjoint closed sets. We then index these nested sets using dyadic rationals, which is honestly just a fancy way of saying fractions with powers of 2 in the denominator. Finally, we define a boundary function to establish strict continuity based on whether a point falls inside or outside these index sets. So by nesting open sets, we gracefully construct a continuous function entirely from abstract axioms. Next up is Brewer's fixed point theorem. This theorem essentially dictates that if you continuously stir a cup of coffee, at least one particle of liquid will end up in the exact same spatial coordinate it started in. Crazy, right? Formally, it states that every continuous mapping from a compact, convex Euclidean set into itself leaves at least one point fixed. Mathematically speaking, there is some point where the output of the function is exactly the same as its input. This proof brilliantly illustrates the power of algebraic topology. The proof starts by assuming the mapping has 0 fixed points. If that were true, we could formulate a continuous retraction, basically pushing everything to the boundary sphere. But then we apply a functor that maps our topological spaces over to algebraic groups. When we do this, the algebra demands that the identity map equals 0. And because that is a blatant algebraic impossibility, our initial assumption has to be false. So, by translating a geometric problem into an algebraic one, the resulting contradiction proves the fixed point absolutely has to exist. Finally, Section 5, Interdisciplinary Applied Topology. For our finale today, let's observe how these highly abstract mathematical laws actually fundamentally govern our physical and digital reality. In molecular biology, life itself literally depends on topological invariance to manage DNA supercoiling and viral genomic packing. The spatial conformation of your double-stranded DNA is governed by the linking number, which is an integer invariant representing how the strands intertwined. This is a product of twist, the local helical twisting, and writhe, the global supercoiling. When your DNA needs to replicate, special enzymes called topoisomerases step in. They act like biological mathematicians, introducing transient breaks to deliberately alter the linking number, preventing the DNA from tangling itself to death. Over in computer science, they use topological data analysis to extract hidden geometric structures from massive, chaotic datasets. By building what we call Vietoris-Rips complexes from massive point clouds, algorithms can sweep across increasing scale parameters. Through persistent homology, we can mathematically track the birth and death of topological features, things like connected components, loops, and voids. This data is then visualized into persistence barcodes, which cleanly reveal the true underlying shape of high-dimensional datasets. It's a real game-changer for data science. In advanced physics, exotic quantum phases actually fall completely outside classical symmetry and are instead classified entirely by topological invariance. Take topological insulators, for example. These are materials that act as perfect insulators in their internal bulk, but are highly conductive on their surfaces, protected entirely by time reversal symmetry invariance. We also see this in the quantum Hall effect, where conductivity is quantized based on a topological metric called the TKNN churn number. And scaling way up, astrophysicists even use cosmic topology to analyze background radiation, to figure out the global connectedness and geometry of spacetime itself. Even industrial robotics relies heavily on this. They map physical obstacles as topological holes on an n-torus to safely plan movement trajectories. When you have a robotic arm with multiple rotating joints, its possible movements exist in a configuration space, which is topologically equivalent to an n-torus manifold. Physical obstacles in the real workspace literally translate into topological subregions that the arm has to avoid. By using path homotopy, algorithms can evaluate if a collision-free path can be continuously deformed to reach the target without ever hitting a barrier. Ultimately, whether you're dealing with pure abstract theory or applied computational science, topology acts as the fundamental rulebook for spatial existence. It provides this incredible unifying framework across modern mathematics, effectively connecting our local Euclidean calculus to global algebraic, geometric, and point set invariants. So it really leaves you wondering, if these abstract mathematical structures define the very boundaries of our reality, are we just living inside one massive, continuously deforming manifold? If the invisible rules of topology dictate everything from the supercoiling of our DNA all the way to the quantum phases of matter, what is the ultimate topological shape of the universe itself?
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.